Okay, let's go ahead and get started. So first off, let me thank you as always for taking a bit of time out of your day to come and learn a little bit about what's going on with Green Bank Observatory, as well as some of the great science coming off of our telescope. I'm Karen O'Neill. I'm the director of Green Bank Observatory, and I'm just going to give a brief introduction here to what's going on with the telescope and all of that. And after that, we'll move on to the highlight, which will be a talk by Helene Courtois talking about cosmic flows in Green Bank and the discovery of the Laniakea superstructure. So with that, just a quick update on what's going on. Of course, COVID-19 is on our minds, like it is with everybody. Within the state of West Virginia, the number of positive tests has been fairly steady for quite a while now. Around 3 to 4% of all tests are positive for COVID-19. Vaccines within the state are getting distributed, so that's going fairly well, with about 40 to 42% of the population is fully or partially vaccinated. That includes all ages. But I will point out that the distribution of the vaccine is slowing. The number of people choosing to get the vaccine is slowing. Hopefully that will pick up again as the state tries to bring some incentives forward, as well as the age for the vaccine is dropping thanks to the FDA. Within the county itself, Pocahontas County, which is where Green Bank Observatory is, we've had very few cases lately, which has been fantastic news. And in fact, are at the lowest point in the entire state of West Virginia for the number of positive cases around in the area. So we're hoping that trend continues well into the summer, as well as hoping that the number of vaccines continues to get out into the general population to really help out both ourselves as well as our communities. So thinking about the Green Bank telescope itself, of course, we remain in full operation. I do say here 24 hours a day, 7 days a week, which is true. Although we have moved into a summer maintenance schedule now. This is an extended summer maintenance schedule this year, going from most of May all the way through the end of September. The reason for that is to make up for some of the lost maintenance that did not occur last summer, as we were still trying to understand proper protocols to work safely underneath the COVID-19 pandemic. But summer maintenance is now underway, so most weeks this summer will be in 4 days of maintenance from Monday morning through Thursday evening. And in this maintenance time, we do all sorts of things, including painting a large part of the structure. We don't paint the entire structure every year, but we get the most important parts, and then slowly over a period of about 10 years, we slowly get the entire telescope painted. We repair the actuators that sit underneath the dish. And this year is the year for what we call our triannual structural inspections. That's when we get an external group that comes every 3 years to inspect the structure of the telescope and to look for any concerns or any issues whatsoever. I'm happy to report that our outdoor tours and demonstrations and presentations and talks are all underway. This is a great chance to walk around the site and get to see the site. And it is a walk, but on beautiful days out, it's a great chance to learn some science and see a lot of beautiful scenery and just get a chance to be outside. Coming up, we have a few things. Of course, we're continuing our community Zooms every other Wednesday at 1 p.m. Our next talk is on May 26th with our own Natalie Butterfield, who'll be talking about molecular gas in the galactic bar. And then the next one after that will be by Sarah Isone, talking about the size, shape, and scattering of Sagittarius star. We also have our observer training workshop coming up. This is at the end of May. That is completely full, and everyone has been notified now whether or not your attendance has been accepted for this. If you didn't get in, don't worry. We've got our single dish school, which also has an observer training workshop at the end of it, happening in the end of September. Those signups open on July 1st, so I strongly encourage you to join that. We are hoping that will take place with Arecibo Observatory to look at some data reductions from some of the data taken there, but that's still a little bit TBD. We'll know that before the sign up on July 1st. So with that, I would like to hand this off now to Jay Lockman, who is going to introduce our speaker today. So Jay, it's all yours.
Okay, thank you. Our speaker today is Helene Courtois from the University of Lyon, and I have lost the title of your presentation, Helene. So why don't you just begin your screen sharing and take over.
Okay, so thank you very much for giving me this opportunity to talk about the science we do with Green Bank. Do you see the presentation full screen? I hope yes. Okay.
Yes.
Good. What we do actually is what is called as a cosmography. So we make maps of the universe, and our specialty is to make maps in motion. So it's cartographing where are the galaxies around us, measuring their distance, and measuring also what we call their peculiar velocity, which is the velocity due to the gravitational field felt by a galaxy. So we try to measure those properties of a galaxy by removing expansion from the radial velocity of a galaxy and being left only with the gravitational potential due to everything, whatever it is, dark matter, luminous matter, things that we don't know yet. And we try doing this to tackle the question of what is gravitation and what is the mass, where is it located in the universe. So I give just a very basic start of the talk. So we live on a planet, Earth, which belongs to our galaxy, which is called the Milky Way, and we live in one of the external places of the galaxy, in one of the spiral arms. This galaxy belongs to a larger structure, which we have discovered and named Laniakea, which is a supercluster of galaxies. And superclusters belong to the huge cosmic web in the universe, so architectures of galaxies that are defined in high-density places, and those high-density places are separated by empty places that we call void. So how do we make a cosmography or cartography of the universe? Actually, first, of course, we go to telescopes. So we use Arecibo that Karen just mentioned to obtain H1 data. We use a lot Green Bank telescopes since almost 10 years, actually, and we had a large program on Green Bank. We use also optical telescopes in space and on the ground to obtain the photometry, surface photometry of those galaxies. And when we have the radio and the optical photometry, we can compute the Tully-Fisher distance. So we use a lot Hawaii, also the 2.2 meter from the University of Hawaii as an example, but we use many telescopes, both in radio and optical. So what we obtain, those are typical Green Bank telescope spectra obtained in our last campaign that went from 2018 to 2020. On the left-hand side of the plot, you can see the optical image of a galaxy with its H1 spectrum obtained at Green Bank. So those pairs belong to all the same galaxies. And you can see that the H1 line has this shape in a kind of M letter. And we measure, this is the H1 line, which is rotating, the galaxy is rotating, so the H1 line is being enlarged. And when we measure the width, we obtain the rotation of the galaxy, which with the optical photometry gives us the distance of the galaxy. I just want to point out that even if this is a targeted survey that we conduct at Green Bank compared to Arecibo, for example, where it's a blind survey, so you don't choose the galaxy beforehand and you don't point to the galaxy in Arecibo. What we do at Green Bank is that we select first the galaxies that would give us a good data point in our sample, and then we observe them at Green Bank. But sometimes we fail, and we have a rate of failure of about 3 to 5% of our sample. So those are examples, these two columns. For example, this one, which was a nice spiral seen on the edge, actually, you can see that in the spectrum that we obtained, there was maybe another galaxy in the reference sky. Or, for example, this one, we thought it was a nice spiral, a little bit inclined. Actually, it's a single peak at the end, so it's a bit difficult to measure the rotation. We also have galaxies that look like spirals on the edge, and actually, probably they are more like a lenticular galaxy. So, of the family of the elliptical galaxies, meaning that they don't have a lot of neutral hydrogen gas left. So sometimes you fail even if you choose really by hand before, and we always eyeball inspection all our targets, but sometimes we don't make it. So once we went to the telescope, obtained our data, so to both kinds of telescopes. So each galaxy requires two observations, at least two observations at two different telescopes. Then we obtained this left plot, which is just the radial motion of the galaxy in the gravitational field. And we have, from these radial motions, we have to compute a reconstruction in 3D of the full volume of the universe. So here, this is the observations when a galaxy, so this is the map in the supergalactic plane, XY. And here, where there is no data, actually it means that it's the Milky Way on the sky that prevents us to observe in these directions. If it's in blue, it means that we have measured a peculiar velocity towards the observer for this galaxy, radially. And if it's in red, it means that it's going away from the observer radially. But what we do is those computations, which are matrix inversions, we transform this in 3D computation of the velocity field. And as you can see, where we have a high density peak, this is Shapley supercluster, for example, you can see that we compute that galaxies and matter. When we do this, we go from light to full mass, whatever it is. And we can see that the matter is falling onto high density peaks. So this is Shapley, this is a Coma cluster and Laniakea and Perseus species. So let me show you this in 3D. Okay, this was a little explanation saying that what we do when we do this, actually, it's just a likelihood. It's a kind of maximum of likelihood. So it's the same as if you see all boats pointing in one direction, you know that the stream or the currents of the water is going in this direction, while when you see it's exactly the same place, it was in Guadeloupe. I took this photo, and here you see that all the ships are in every kind of direction, and it means that the current underneath are not correlated. So what we are looking for, it's very places with a high correlation of motion, telling us about the gravitational field. So in 3D, so this showed us, that when we colorized the streamlines, so the stream that we computed, we could see that there were two different parts in the local universe. We live here near Virgo cluster. And actually, we had one big blob of streamlines that we made in red and another big blob. So at this point, we decided, so this was in 2014, so this Cosmic Flows program started in 2006. So now we are 15 years into the program, and you will see that it's not over yet. Actually, what we have seen, because it's in 3D, as I told you, so we have this data cube of universe where all streamlines are computed. I hope it's not lagging too much, and that you will see the rotation of the universe. I'm not sure that it's not lagging, actually. Is it lagging? I think it is. So maybe I can make progress by hand on the movie. Okay, it's not really working. Okay. No problem. It's just I wanted to show you that we are not doing this in one plane. And if we take only these streamlines that were in black, actually, we can identify a full volume in 3D, where all galaxies that are inside this volume have a motion, a current motion towards the inside of the volume. So what is in blue, this small surface in blue, fade surface, actually, when a galaxy is inside this surface, it belongs to the supercluster. When it's outside this surface, it's falling onto the next attractor. So it belongs to another supercluster. So by doing this method, where we have been using terms used in hydrography, so watersheds, gravitational river, we have totally changed the concept of what was a large-scale structure before. Actually, before you had this, for example, this big line, every white dot here is a galaxy. So you had this line, this filament of galaxy, and you could say maybe, okay, this is one filament. And there was no way of saying, no, I don't think so. I think that this filament stops here, and this belongs to one structure, this belongs to another structure. So now we have a full dynamical definition. And Laniakea is the place where we live. In Hawaiian, it means immense heaven, because actually it's 100 times bigger than what was thought before to be the local supercluster. So the local supercluster, by the time of Gérard de Vaucouleurs, the first guys working on a large-scale structure, they thought that the local superclusters was here, so the place of the Milky Way, up to Virgo. So this was the place of the local supercluster. If you hear the Virgo supercluster, for example, this is a wrong terminology, wrong definition. Actually, it's much bigger, and it encloses about 1 million galaxies. And now we are mapping the nearby ones. So I can show you, so this is another view of what we call, so we just have changed the colors between Laniakea and the rest of the universe. And I just want to show you how fast we progress. This is in 5 years. 2014, we had the central map. So we live here. So we are at the center of the map because we measure distances from us to other galaxies. And 2019, you can see that we have enlarged by twice the distance. So this means by 10 the total volume that is mapped dynamically. What we can do, we can push it a bit further. We can compute the shear tensor of the velocity field. This is what we call the V-web instead of the cosmic web. It's the cosmic V-web, meaning dynamical web. And actually, you can explore it, and you find kinds of highways of galaxies. So it's like a little Pac-Man. So all this is accessible on the internet freely. And you can travel by yourself inside all the arteries of the local universe. And what we have found by doing this, what we compute, it's this. So we use about 18,000 galaxies in a place where there are about 200,000 galaxies known in Redshift survey, for example. So we don't use all the galaxies, we use very few of them for whom we have measured the distance and peculiarities. But when we overplot all the galaxies that we know in the local universe, guess what? Actually, they are all inside the arteries we had computed out from our small sample of 18,000 kilometers per second. So this means that this methodology, finding highways, little countryside roads, so actually finds the place where the mass is, at least the luminous matter is, the galaxies. And we think that we are confirming the standard cosmological model, where the dark matter and the luminous matter are located roughly at the same place. So what we can do also, we have answered a few questions along the way. Where are we? Where are we going? And maybe we want to know where do we come from? And this is also quite easy because all these architectures are created by the tug of war between expansion and gravitation. Think in your head, if you had only gravitation from the start of the universe, actually all the matter would be in one blob at one place. If you had only expansion, all the universe would be totally dissipated, dispersed, and there would be no this kind of filaments, walls, bubbles that we see. So actually we need both, and we need them in a certain amount so that the universe can grow and arrive at this mature level where we can see Laniakea, Coma, supercluster, Perseus species. So nowadays, with the peculiar velocity field that we have computed, we can go back in time. We have coded a reverse back in time machine, which is called the reverse Zeldovich approximation. You go back in time, we launch particles with these initial conditions, the velocity field, and actually you recreate universe, an artificial universe, but that looks very much alike the universe we are observing at the telescope. So what's next? What we are on to right now? As I said, so from Cosmic Flows 3, we are going now to Cosmic Flows 4. So it's the fourth generation of catalog. Cosmic Flows 1 in 2018, we had 1,600 galaxies, the ones in yellow. Then we had 8,000 galaxies in Cosmic Flows 2. This was in 2012. Then we added up all those galaxies that made the Cosmic Flows 3. So those came from Australia, from the 6DF survey. And we added the green bank here in red. Those ones are added up. And at the moment, we are, so this split is between the northern skies and the southern sky, I mean terrestrial northern. And you can see that we have many more data in the south than in the north. Actually, we are lacking telescopes in the north. But using Arecibo and using SDSS, this is exactly what we are doing today at the lab. We are trying to use the optical spectra high resolution from SDSS to compute the fundamental plane for those galaxies and add them. But as you can see, this is totally asymmetric. And you know that SDSS is a kind of pizza slice. It's not a 3D volume, not a big 3D volume. So it's going to be a bit complex to analyze, but we are adding data nearby and we are going further. So what's next after Cosmic Flows 4, which is almost ready, that will be out by the end of 2021. Actually, now all the southern sky, so this is this gray shaded area, a bit more than the southern sky, are going to be completed by Wallaby in Australia, by Meerkat in South Africa. So Meerkat is going to observe really this zone, the zone of avoidance here, and by Taipan. So Taipan is an optical multi-fiber on the Schmidt telescope at the Anglo-Australian Observatory. So the telescope that made 6TF before was green points here. Actually, all these are going to reach this distance that we call 300 megaparsec over h. So it's 30,000 kilometers per second in the expansion, or z equal 0.1. Actually, z equal 0.1 is what we call the local universe. After that, it's something which is too difficult to do from the ground. There start to be evolution from galaxies here, and after z equal 0.1. So once we have completed this distance, then it's where we are. So in the north, things have still to be imagined. So we need to see if we can push further GBT, if there is a next generation telescope at Arecibo, if the telescope in China, the huge FAST telescope, is giving good quality data and that we can start observing. And this is where we would complete the observations in the north. And also if there is so those Wallaby and Meerkat are SKA pathfinders. So maybe once we will have a full SKA, we can see what we can do. So this will be my final slide. I just said very fast that the main question that we are asking is what is gravitation, which is one of the 21st century question, and the one who finds the answer will have the Nobel Prize, no doubt about this. So actually, using computing peculiar velocities helps us to compute what we call the growth rate of structures in the universe. And what we do, here you have the growth rate, and here you have the span in redshift. As I said, the local universe, we try to have data up to 0.1 in redshift. And those lines here, dotted lines and the solid line, and those ones are all different models for gravitation. The solid line is the one that we know best, the one of Einstein, general relativity. But as you can see, the current data that we are spread a little bit everywhere with huge error bars. What's coming up now, on the nearby universe, there are many experiences starting with Taipan. As I said, our Cosmic Flows 4, we will try to get several measurements of the growth rate. So I put in red the things that are not yet observed. And on the IZ, we have Euclid, which is a space telescope which is going to be launched next year in September 2022. And we hope that we'll have this kind of small error bars on a very large extent of redshift, but still you need both sides of the redshift to be able to determine if this is really the model for gravitation. Of course, here are the most easy and understandable models, but there are some very eccentric and exotic models from gravitation. So at least we try to tackle from two sides. And the curve that we find here or that we find here needs to meet at some point. If it's not meeting, then we have some problems. So I'm going to stop here so that we have time for questions, and I hope it was clear enough for everybody.
Yeah. Thank you very much for a fascinating presentation. I will invite people to submit questions using the Q&A tool at the bottom of the screen. And we'll wait a moment for questions to come in.
Okay. Maybe I will try to relaunch the animation that didn't go through.
Okay. Barry, could you please? Okay. We have a number of compliments coming in the chat window. Very nice study. Thanks for the presentation and so on. So I will. You made a mention of the correlation between the dark matter and the luminous matter.
Yes.
And that comes from your locating the luminous matter through the distances and positions of the galaxies, and then the dark matter through the flow that's correlated with the luminous matter.
Yes, totally. So if you see on this plot, the little white dots are the galaxies that we measure in redshift surveys. So very easily we can try, we have an approximate distance for those galaxies, so we can plot them on a cartography. But the color coding here, for example, the green, the red, the blue, it's the density of matter that we compute from the velocities. So the velocities, it's like slopes of ski, and from the gradient, so from the slope of the velocities, if it's very flat, you know that you are not in a place where there is lots of motion. If it's very steep, you know that there is lots of matter in this direction. So when we have, I'm going to show you just the next one. When we have very high gradients in velocity, it means that we have a huge bunch of matter. And actually, just by eye, you can see, for example, the coma cluster, which is up here. You can see that in the redshift survey, so now the redshift surveys are in black, you can see lots of little black points. Those are the galaxies known, so the luminous matter, and the red contours, it's where we have computed that there is lots of mass, whatever it is. But when we compute this mass, we need 5 times more mass than what we see in luminous matter. So this is where we say, okay, dark matter is maybe a good model. So we don't know if it's a good model or if it's gravitation that we need to tweak. But anyway, what we find is that all the peculiar velocities tend to show mass where we also see luminous matter. I can give you another example doing the reverse, where so I don't go here, the zone of avoidance, it's here, so we don't know galaxies. But if I take this one here, if I plot all the galaxies that any observer has observed at some point, actually I don't see many. in this direction, if you can see. And when I compute with the peculiar velocities, actually in this place, the velocity field tells me, no, there is no matter in this direction. So we see this correlation by eye, like this on a map. And we also see it when we compute all these gravitational fields with just our measurements of motions, and that we try to look where is the luminous matter, and we always see it not outside. Every car is on the road. It's like you don't have a car going through a field. All the galaxies are inside the highways and the streams. And
Okay, we have some questions that come in. The scatter in the TF and FP relations relates to distance uncertainties.
Yes.
How tied should these relationships be to, it says, I think it is, how useful are these relationships at a redshift of 1/10, 0.1?
Yes.
Does averaging the galaxy sample help?
Yes, it's the worst nightmare. It's our worst nightmare. So you push the right button. So the Tully-Fisher relation, which is for spiral galaxies, and the Faber-Jackson or fundamental plane galaxy relation, which is for ellipticals, has errors of about 20%. And sometimes for the 6DF, for example, sample, we were up at 27%, and it's not exactly proportional, but it goes with the distance. So the further we go in our measurement, and the less accurate our measurement, our distances are. Even if the spectra are, I can tell you a spectra at 0.1 of Z, it's excellent, just as a spectra at 10,000 kilometers per second, be it in optical, be it in radio. If you have enough exposure time and good resolution, it's not the data at the telescope, the problem. The problem is exactly what the reader just said. It's the scatter in the relation. So how do we handle this? First, we try to recalibrate the scatter at different bands, trying to find where it is better. For example, Tully-Fisher, at the moment, we are going to space near-infrared photometry with the WISE telescope bands, which gives us a relation, a Tully-Fisher relation, which is better. Just before we were using the I photometry and the K bands on the ground that were much better than the 20 years ago. I was using B and V photometry, for example, and slowly we try to get a better scatter. And also, we try to also obtain a better inclination of the galaxy. So at the moment, we had a huge citizen science participation to help us find a way of measuring the inclination of galaxies. So we try to tackle every little bit. And then at the end, we still have this Malmquist bias that it's in the game and that we have to handle. So what we do now, and I have seen it in many conferences across the world, we try to forward model the data. So instead of just applying straightforward the distance that we have computed to the peculiar velocities, actually we try to understand if this distance is coherent or not with the location, with the other galaxies around. We try to do all this Bayesian forward modeling, which is really in all the fields of astronomy. I can see now young PhD students coding this kind of forward modeling of the data, which helps a lot after the reconstruction, the 3D reconstruction. But up to Z equal 0.1, so CF4 will be the first real test with using the SDSS spectra, but I'm pretty sure, and we have made models when we applied for Wallaby for the SKA Pathfinders, and we are pretty sure we are in good shape of doing this up to, yes, 30,000 kilometers per second with Wallaby, with Meerkat, and you know they have a very high sensitivity, those radio telescopes. So with better data, with better modeling of the data, with better handling all the different places where we can lose a signal to noise, I think we can do it.
Okay, thank you. There is a link in the chat to the interactive version of your some of your plots
cool.
and answers to one question. And another question is, it has to do with the Hubble tension, one of the big
Yes.
modern cosmological problems.
Yes.
Could you comment on the modification of the local Hubble constant as affecting your solutions, or does it?
Yes. So with the Hubble constant, for example, our field is maybe not the most accurate field to produce a Hubble constant, because what we use is a mean Hubble constant of overall the full volume. Still, when we have the raw data from the telescope and we start to compute distances, so without using too much Hubble constant, and that we look at it, we arrive at a value of 75 kilometers per second per megaparsec. But after the forward modeling, this value goes down to 72, for example, kilometers per second per megaparsec, which is more or less our favorite value at the moment. If you look at the cephalids, for example, Wendy Freeman, these huge key projects on the Hubble constant, I think they are around 71 kilometers per second per megaparsec. So everybody who is really measuring a distance, and even the supernovae, they were lower, they were at 69 kilometers per second, but they found out that supernovae, of course, are not standard candles, and you have to take into account the place where this supernovae bursted. So it means the place where the progenitor was born. So for example, if it's a place in the galaxy with young stars, or if where the supernovae burst, it was a place with no stars or gas or whatever. So now they can see that there is families of supernovae type 1a. But when they take this into account, from 69, they go up to 70, 71, actually. So everybody who is measuring a distance, we are in a much better shape in terms of tension than we were, let's say, 5 years ago. It seems that everybody starts to understand its own sample, actually. But when you compare to experiments who are not measuring distances, for example, the CMB, be it the Planck data, WMAP, I don't know, some all CMB experiments, you know that the Hubble constant from those experiments, actually, it's a parameter of the model. It's not a measurement. It's not an observational measurement. It's a model with 26 parameters, usually, or 41 parameters, depending on the model of WMAP, Planck, etc. And then some parameters that are believed to be the Hubble constant comes out, and they are at 68, 67, I think the first one, 68, for example, and this is too low, totally incompatible with what we see in the local universe up to supernovae, which are a bit further than z equal 0.1. So this is the main tension. What we think, how we interpret this tension, apart from everybody has to work on its data set to understand it, we think that those measurements are global measurements. So it's on all the sky, WMAP or Planck or whatever CMB experiment, and it's integrated on the time, because when you see a map of the CMB, people say, look, you are looking at the inhomogeneities at the time of the Big Bang. No. You are looking at things that went through all the universe up to your eyes. So there are lots of things happening on the line of sight of integration. And when you measure an H, and I don't call it an H naught, because it's not a Hubble constant now and here in the universe compared to the other experiments. It's an H of T over XYZ. So meaning to me, it's my understanding, but I'm not a CMB professional. I mean, I would like to use those experiments in certain places, in certain directions, and with less integration, or in places where we understand totally the integrated Sachs-Wolf effect, for example, on the sky, and compare them to the same places or the same direction when we compute an H naught. And then maybe we would understand about this tension. This is one direction that we can still study. And I can't say much more about the Hubble constant than all those thoughts that people have at the moment in various conferences.
Okay, thanks very much. We still have some questions, but unfortunately,
Okay.
we need to bring the session to an end. So let me suggest that those who are listening and have questions contact Dr. Courtois directly.
Sure.
Thanks again for a most interesting and enlightening presentation. And I would invite everyone back. The next two speakers are dealing with the center of the Milky Way. So we'll come in quite a bit closer to home, 2 weeks and 4 weeks from now. Thanks again for joining us today.
Okay,
Goodbye.
bye-bye, everybody.